the same amount of Skittles. But some Skittle flavors are not created equal.
You almost called me.
Well, they just called me right now. I don't know. Maybe this is you. Who's in trouble now? The phone's ringing. It's Rega's room. Yes, I do. Okay. All right. Nicole, they need you in the main office. Let's write this out real quick just in case, because he almost got caught by a security guard, apparently. And I don't want to get myself in trouble. 7:26. There we go.
Thank you.
Cool. So anyway, at some point, just so you know. But anyway, if you're like splitting up some Skittles, like not all Skittle flavors are created equal. For example, name your favorite Skittle flavor. Green's the best, red's the best, right? So now I'm just saying, if I had a bag of Skittles, would it make much sense for me to just randomly split the bag evenly amongst the class if you favor green and she favors red? Doesn't matter. My point being that in fair division, there is a way of divvying up items, whether it be Skittles or objects or whatever, in such a fair way where everybody gets a little bit more than what they were expecting. But anyway, that's just another example of it. We also go over the Fibonacci sequence. We also go over something called the four-color theorem, which is like the idea that imagine a map of the United States, and you get to color the United States. But you can't use the same color on states that share a border. You know what I'm saying?
Yeah.
And you only have 4 colors to do the whole map. But it is possible. It is mathematically possible. That's those are just some general concepts that we cover throughout discrete math. It's not too bad. It's like coloring. Anyway, so today I have you. Tuesday I have you. And then we are on winter break. Now, progress reports are due today. I've already submitted them, but obviously grades can be updated along the way. I will be assigning you various things through Google Classroom, but again, that remains to be seen. As for today, I want to focus on two main things. Number one, I want to do a little bit more with poker or 5-card poker hands. And then number two, I want to show you something in the graphing calculator that is going to help us solve some future problems, which is why I mentioned the Chromebooks earlier. Obviously, you will need the Chromebook at some point in order to access your graphing calculator because I want to show you how to use certain things. So if you would, if you do not already have them out, I'm going to need those notebooks out and open. Let's see here.
I wake up in the middle of the night, yeah.
Oh, yeah? That's good. One day you're going to be like, when was the last time I heard that?
That is true.
Oh. Where are people today? Oh, I never submitted a homeroom. That's why. Boom. There we go. There we go. Poker. There it is. So, before I get into these details, I just want to show something right here. This is a Wikipedia page called Poker Probability. Oh, there he is. Aha! Ah! Almost got him. Anyway. All right. This is a Wikipedia page entitled Poker Probability. Now, what's really nice about this is that they give you some very basic things. For example, the concept of a royal flush. Now, with a royal flush, I'm looking at the frequency right here. The frequency being 4. There are 4 ways that you could potentially be dealt a royal flush. A royal flush being the ace, king, queen, jack, 10 of the same suit. There's only 4 ways to do it. And they give you the probability of such an event happening. Now, I'm going to ignore cumulative probability and odds against, but I'm going to be focusing on mainly 4 things in these charts, just for a brief moment. The frequency of it happening, the probability of it happening, and this, the mathematical expression of absolute frequency. Now, this is actually what we did last class. It just doesn't look like what we did last class. Last class, I introduced to you, or not introduced, but kind of explained the concept of NCR. That is finding the number of ways that you could get 4 objects, R objects from a group of N. That's what this is. This is nothing more than 4C1. It's just an alternative notation that you may see written. And of course, I'll get this into our notes when we actually get there. If I scroll down a little bit, I'm going to scroll down to full house, because that's what we did last time. In your notes, what number do we have written down in our notes for the number of full houses that we could get? I did say I had those notes out open, right? How many total full houses could we have had? We calculated it on Wednesday. This number right here. It's exactly that number right there. That is exactly how we calculate such a thing. Now, the percent chance of that happening is pretty intense. It's a very small chance of that happening. And of course, here's the calculation behind it. He did. So did the other guy. Yeah. Now, obviously, with Texas Hold'em versus 5-card poker, right? Good call. Where's my deck of cards? In regular 5-card poker, depending on how many people that you're playing with, because there is a maximum number of people, they have the deck of cards, which is completely randomized, and they deal you 5 cards. 5 cards total. Everyone's dealt 5 cards. There's a round of betting, and then there is an opportunity to replace certain cards in regular 5-card poker. So if you get these 5 cards right here, I don't even know what I got a pair of kings, right? Perhaps I don't want people to know that I have a pair. Maybe I don't want people to know that I have a pair. Maybe I want people to think that I have something better than a pair. So perhaps I might hold on to the king, 10, and I might discard the 6-8. So I discard this, not showing anyone what it is. And they would deal me 2 brand new cards, which may or may not help me. I don't know if they did. Maybe they did, maybe they didn't. Clearly it didn't in this hand.
So you could literally just drop your cards at any point, turn around.
It has to be your turn.
Hopefully.
It has to be your turn. So like, for example, if there's 5 people around me, whatever, it's like, okay, I go to this guy. How many cards do you need? 2? Okay, I take the 2 from you. I give you 2 new ones. Next person, how many cards do you need? Oh, I need 1. Okay, here, and that kind of thing. But it has to be like fresh from the deck. Yeah. In Texas Hold'em, it's a little bit different. Can't do that. You get your 2 cards, and you can't change anything about those 2 cards in Texas Hold'em. And then the community cards in the middle belong to everybody.
I feel like Texas Hold'em is probably more fun, right?
It's more popular. It is the most popular version of poker that there is. Yeah. In fact, at the World Series of Poker, there are dozens and dozens and dozens of poker-style events, but there's only one main event, and that main event is Texas Hold'em. Yeah, traditional Texas Hold'em. I know, it's really weird, isn't it? Yeah. You should. The side events are interesting.
I was actually after class I was just bored. And I started playing like on the computer.
Yeah.
It's actually pretty fun.
It can be. It's fun to play against like real people, and obviously some people consider it even more fun to win money. But I'm not promoting gambling because I don't I don't. But it is fun to play against other people, to kind of outwit other people, to outsmart other people. So what I want to do is I want to prove something. I'm going to zoom in just a tad right here just to kind of cover something up. There we go. Perfect. And I'm going to scroll down to something like this. 3 of a kind. There we go. 3 of a kind. Now, 3 of a kind, according to this, now I'm hiding how they're calculating it, because we are going to have the opportunity to calculate this in a few moments in our notes. But 3 of a kind, just to get 3 of a kind, means that you have 3 cards of the same kind, and then you have 2 other cards that do not match. They don't match the 3 of a kind that you get, meaning you can't have any more queens, and the 2 cards that you get cannot be of the same kind. They can't be like a 5 and a 5, because then it wouldn't be 3 of a kind, it would be a full house. It can't be like a queen and an ace, because then you wouldn't have 3 of a kind, you would have 4 of a kind. And the number that I am interested in is this number right here, 54,912. That's the number that I'm interested in. I'm just going to leave that on the board, because we are going to have the opportunity to try to use our combination formula, our NCR, to figure out that number exactly. So you do have your notebooks out and open, and I do see some of you have your Chromebooks out and open. Please make sure you do also have your Chromebooks out and open, because I want to make sure you see how to utilize the NCR function in your calculator. I'm going to flip over to my notes. What is this? I don't know who that is. Cool. I'm going to flip over to my notes here. Click. Today is the 18th. We're going to wrap up with some poker hands, but then we're going to get into something else afterwards. So this is poker hands continued. That's just continued right there. First, I do want to show you that one thing about NCR. NCR, which, as we talked about, is getting a combination. Basically, it's how many ways to get R objects from a group of N, could also be expressed like this. It could also be expressed like this. Now, it's very strange how they pick and choose what notation to typically use. But I just wanted to make sure that you guys saw exactly what we need from this little thing right here. It's very strange. So again, just as a thing, how many here? I got 5, I had 6 students here. Okay, just for the sake of argument, again, if I had 6 students to choose from, and let's say that I had to choose, let's say I had to choose 3 of them. Let's say I had to choose 3 of them. So there's 6 of you, and Nicole will be back in a little bit, but there's 6 of you. Without using a calculator, without using any type of means of calculating it, could you just guess a number, estimate a number? How many different ways could I choose 3 of you? I mean, clearly it's more than 1. Because I could pick like the first 3, I could pick the last 3, I could pick them. If there are 6 students, which there are with Nicole, if there are 6 students, how many different ways could I select 3 of you? I could pick the first 3, I could pick the last 3, I could pick the middle 3. I just named 3 different ways right there. Yeah. I could pick every other person. I could pick every other person from the back. There's a bunch of ways, but how many ways? This is where, again, I'd go to the Actually, no, I'm going to bring up this calculator. I'm going to bring up this calculator because I do like it a little bit better now that I've gotten used to it. The TI SmartView CE. Not that I'm advertising. But again, if you were to go math, prob, NCR. By the way, when you guys do this, I just, for my own sake, when you guys do this on your Chromebooks, does it pop up in the same style that you see right here? Or does it come up slightly different?
How would you add the second?
No, you just hit math,
Oh, just hit math.
hit math, tab over to Prob, and hit NCR. Does it show up in the exact same style? Okay, good. Now, on the 83, on this old calculator, it does it differently. I'll show you that in a minute. But if I were to type this junk in, 6, 3, boom, there's 20 ways to do it. 6 students, I got to pick 3 of them. There are 20 ways to get that done. Isn't it? There's 20 ways to get that done. Now, we could list them out, but it actually wouldn't take that long. It would not take that long to list that out. Which is kind of nice, actually. But that's not what we're here for right now. I'm here for something else. We're trying to figure out 3 of a kind. Say who? Whatever. I'm here because I want to be here. Can you believe they pay me to do this? Joke's on them. I do it for free. 3 of a kind in a game of poker. Now, to get 3 of a kind, just to be very clear, oh, someone get that? 3 of the same kind and 2 other cards that don't match. So just to be very clear about 3 of a kind,
Royal flush is all the cards, they all have to be the same suit.
a royal flush, they have to be the same suit, and it has to be the ace, king, queen, jack, 10. That's a royal flush. A regular flush is they all have to have the same suit. A regular straight would have to be just cards in order like 5, 6, 7, 8, 9. Or 8, 9, 10, jack, queen. But 3 of a kind, you have to have 3 of the same kind, but keep in mind 2 other cards that do not match. Now, they could match in suit, but they can't match in terms of kind. I should say don't match kind. So let's talk about the 3 of a kind. I asked you this question, and we wrote this down a while ago when we were talking about poker hands. How many different kinds are there? There are 52 cards. There are 4 suits, and there's 13 kinds, as he just said. There are 13 kinds. And again, just for the sake of argument, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. There's 13 kinds. So if you have 3 of a kind, this combination right here picks the kind. It picks the kind of card that you're going to have in that 3 of a kind. It's kind of like a little bit of a puzzle here. From there, we have to pick the 3 cards. Because, I don't know, like, how many kings are there? How many kings are there? Yeah, there are 4. How many aces are there? There's 4, yeah. There are 4 4s. There are 4 10s. There are 4 jacks. There are 4 in that particular kind, but you only need 3 of them. That's what that next calculation does. This picks 3 of the 4 cards. That calculation would pick 3 of the 4 cards. Because again, as I tried to show last time with my little deck of cards that I had, the general idea, and I guess I could go back. I can go back here. I'll do it with the 10s. I'll get the 10s and I'll put them underneath the scope in a moment. Oh, I thought the 10s would be easy. Where's my last 10? There's my last 10. Good. I got my 10s. But if I have these 4 10s right there, if I have 3 of a kind, I don't have all 4 of them. One of them has to go away. So maybe I got that one. Or maybe I got that one. Or maybe I got that one. Or maybe I got that one. Instead of trying to figure that out by hand, I let the combination do the talking for me. So now I have to pick the other 2 cards. I have to pick the other 2 cards. But they can't match. They can't match each other. This gets a little tricky. Look at this calculation right here that I just wrote out. Look at that calculation that I just wrote out. I want to talk about why that is. So now, if I have that combination, I want to ask you a couple questions. What in the heck does this number represent? Say again? Not the card away, the kind of card away, yes. The 12 represents the fact that I'm no longer picking from all 13 kinds. I'm picking from 12 because I can't use the same kind that I had before. So for example, where's my deck of cards again? Come on, deck of cards. If I chose these 3 10s right here, boom, those 3 10s were chosen using these 2 combinations, picking the kind of card that we were going to get and picking 3 of the 4 cards. But now I can't pick 10 again. A 10 cannot show up in the remaining 2 cards. It can't. So there are 12 kinds left to choose from. But then you end up choosing 2 of them. You have to pick 2 different kinds from the remaining cards. Pick a kind of card that's not a 10. An 8 and a queen. 8 and a queen. There's an 8. There's a queen. All right. I got the 8 and the queen. Hold on. Where's my extra little clippy thing? There it is. I knew I had an extra clippy thing. Chapow! There's my queen. This combination picks 2 brand new kinds out of the deck. In this case, 8 and queen for our example, but it could be any of the 12. We just chose those 2 for the fun of it. This calculation, like I said right here, this picks the 2 remaining kinds. That picks the 2 remaining kinds. Now look at that. That picks the 2 remaining kinds. And now I have this calculation right here. What this does is, well, you said 8 before, right? How many 8s are there? There's 4 of them still in the deck, right? I only need 1 out of the 4. And you said queens. There are 4 queens. But I only need 1 out of the 4. That's what these 2 remaining calculations do. Here's what I want you to try. You have your Chromebooks. You have the calculator on your Chromebook. You do need to get the practice with typing this stuff in. So I'm going to ask that you do take a moment and actually try to calculate this thing. Now, like I said, if you go math, prob, NCR, you can type in something like 13, tab over for the 1. And then you want to get the next one, math, prob, NCR. Now, if you notice right here, something got a little messed up here. You see what's happening here with this thing? Oh man, if only there was something in mathematics that could save me. If there was only something that my Algebra 2 students would remember that I said all year long that would save you. Do you not remember? You remember notebooks out and open, but you don't remember what's going to save you? Parentheses are going to save your life. I would think so. Parentheses are going to save your life. Now, with this thing right here, this calculator, I'm not terribly happy with, but this is the one that you guys are working with, right? Yeah. I'm not terribly happy with how this calculator functions. But look what happens when I do that. I put parentheses around the 13C1, and then I open up another set of parentheses and I start typing that thing out. What I want you guys to do, take a moment. I need you to get the feel for it, get the practice with typing it into the calculator. I need you to get me my final answer. I want you to see it, and then I'm going to show you what it should look like here. So take those 5 combinations, take a minute or two, and actually try to type it out. I want you to type out those 5 combinations in parentheses and hit enter. See what happens. There are certain times in which they may also show it like this. But it's the exact same calculation. What? Oh, 5 of them. I know. I mean, just for the sake of argument, I think that if I were teaching from home, it'd be a lot easier to see everything because of the setup that I have at home. Just saying. Say what?
5, 4, 9, 2.
So that's what I'm saying. Now, here's the thing. In poker, the question then becomes like, okay, what would win? Would flush win or would a straight win? Would 3 of a kind win or would 2 pair win? Nobody just picked it. They calculated the number of ways that it can happen. And whatever happens less often is the stronger hand. That's the way they do it.
Wait, I have a question.
We'll take a look. Hold on, looking at it.
Okay, so what are we doing this? Am I going to?
Open up another set of parentheses.
Oh, okay, again, okay.
Yeah.
I don't know if I can enter and do it.
Technically, you could. I mean, honestly, you could do it one of 2 ways. You could hit enter and then just get the number and then do it for the rest of them and then multiply those numbers together. Or you just open up another set of parentheses and you can keep going from there. What's up? Oh, okay, your calculator. Okay, hold on. Yeah, this one, it's going down on a slant. Something went wrong here. Let's go back here. So, hold on. That's the way that you want it to look. They should be like all level with each other. I don't know. Honestly, I don't know why it was doing that. That was strange though, but I can see why it wouldn't work. technically, like I said, I am. That's cool. Technically, like I said, you could type in this stuff like this. Yeah. Gotta make sure things are in the right location, of course. Delete that. Close that. Open up that. Math. Prob. Third one. 12. Go over. Put the 2. Close that. Open it up. Math. Prob. 3. I prefer having the actual calculator in my hand. Yeah. But unfortunately, these are the circumstances. It is? After you type everything in, before you type in the next parenthesis, do you tab to the right? That's strange.
It
Because
might look like that, because mine looked like that. Like going on the side, but then it even felt that.
it did?
Yeah, well, like, the parentheses are getting smaller and smaller, but then once I click the next one.
Did you get 3,432?
54,912.
Yeah, that's it.
Yeah.
I literally typed in the same exact.
I think that's what's messing it up, though, is the slant. Can I borrow the calculator? Because I could actually kind of show visually what's going on with that. Come on. Oh, your battery's almost dead. So you can see CRE 13C1. Now let me zoom in right here. Boom, Chapome, and Chateau. Let it focus for a moment. There, zoom in a little more. There we go. Okay. So you see that little arrow tab thing there? Let me just see what happens. If I type it there, no, I definitely don't want that. If I go over to the right and hit that, it closes it, right? And then if I hit the parenthesis, it does that little tiny parenthesis. That's fine for now, because if you go math, prob, NCR, it does even out on yours, right? So then the 4-3, and I tab over, close it, open, math, prob, NCR, 12 and a 2, boom, boom, math, prob, NCR, 4 and a 1, boom, boom, math, prob, NCR, 4 and a 1, boom. That's what it really should look like.
You know what I wasn't doing?
What's that?
I wasn't going up and then doing the parenthesis. I was finishing I would do 13C1, and I wouldn't go up before I hit parenthesis. I would just hit parenthesis.
That's probably what was causing it. Yeah, that's probably what was causing it. But that 54,000 number, 54,912, those are the number of different ways that you can get. Those are the number of different ways that you can get 3 of a kind. It's very strange how they go about doing this kind of thing. Here, let me flip back here. Nope, to here. There we go. Zoom back out. There we go. I love this stuff. Like now, no, that's the 7-card poker. I don't want 7-card poker. It's a variation. There we go. 5-card poker. Now, what's interesting about all of this, again, is like right here. If you're playing poker, specifically 5-card poker, there's roughly a 42% chance, that you would get 1 pair. Just kind of messed up. And this is how they typically calculate it. It's very similar to what we just did. It's like, okay, well, I got to pick a kind of card. I got to get 2 of those cards, so I have that pair. But then I need to make sure my remaining cards, none of them match. So there are 12 kinds left to choose from. I got to pick 3 of them, and then 4C1, 4C1, 4C1. But look at this junk right here. You have just over a 50% chance of having nothing in your hand. Have you guys ever heard the expression, the house always wins? Never? All right. I talked about being in a casino before. I've talked about like the fact that they take away your cell phone signal, they take away the clocks from the wall. It's designed to keep you in and keep gambling. The house, that's why I have a watch, you know. But if you're in a casino, like the house always wins is the idea that, oh man, this guy walked away with $10,000. Great. These 50 people all dropped 1,000. You know what I'm saying? So if these 50 people dropped 1,000, the house won $50,000, but they only had to pay out to this guy $10,000. The house always wins. Having a casino, if it's run properly, is one of the best money-making ventures you can have. It's really messed up. Oh, goodness. Poker, poker, poker. Okay. Like I said, I did want to show you something else today. We are going to revisit poker in due time. But I did want to show you something else today just to kind of wrap this up. It's a little bit of a distribution. There it is. Okay. I have a die right there. Now, this die is not a typical die. It doesn't have a 6. Instead of a 6, it has a 0. But no worries. Everything else is pretty much the same. Okay. I'm going to roll this die. I don't know. I'm going to roll this die 4 times. What are the chances, or what is the probability that if I roll this die 4 times, that I would get a 3 exactly once? What are the chances? I'm going to write this on the board to kind of like exemplify this point. And I'll repeat the question. What are the chances that if I roll this die 4 times, so I'm going to roll it 4 times, I'm asking for the probability of getting a 3 exactly once. First of all, if I just roll the die, what are the chances that I get a 3 just on one roll? What are the chances that I get a 3 on one roll? Not until I write it down. What are the chances that I get a 3 on one roll? 1 out of 6. Cool. What are the chances that I get a 3 on the second roll? Just on the second roll. Still 1 out of 6. The odds don't change on the die. The odds don't change. From one roll to the next, the chances of getting a 3 don't change. Now, I'm going to roll this die 4 times. I am going to roll this die 4 times. And every individual roll, you have a 1 in 6 chance of getting a 3. Cool. But now I'm going to roll it 4 times, and I want to know the chances of getting a 3 exactly once. Well, come on. Let me do something here. So, rolling a 3. Rolling a 3 in 4 chances. I could get... Now, mind you, I'm going to put a Y for yes, a 3, and I'm going to put an N for no, not a 3. Those are the 2 possibilities. I'm going to do a yes for a 3, or a Y, I should say, and an N for no, not a 3. Yes, I know that there are 6 possible outcomes on a die, but I need to set up my scenario like this for a very specific reason, which I'm going to share in a little bit. So when I roll that die, it may be a possibility of getting, yes, a 3, but then a no the rest of the way. But, as always, that's only getting it on the first roll. I could also get it on the second roll. I could also get it on the third roll. And I could also get it on the fourth roll. These are the 4 possible ways. The 4 possible ways that I could potentially get a 3 on one of those 4 rolls. Say again? Of course you can. And that's actually the scenario that I got to get into. That's actually a definite scenario that I have to talk about in a little bit. But just for the sake of argument, if I'm only going to get 1 3 exactly once, then these are the possible outcomes right here. Because of the possible nor'easter that could have impacted this area, and the fact that teachers don't all live within 5 miles of the school.
Well, it actually did, because my girl went back there.
Sorry.
Yeah.
But anyway, for example, I know teachers that live like an hour north of here, and they got hit with like 10 inches. So, yeah,
Everybody was going 10 miles an hour.
I got you. Now check this out. Check this out. 1 out of 6, 5 out of 6, 5 out of 6, 5 out of 6. Hold on. Let's finish up with this thing. I'm not talking about her rowboat. Let's talk about this. What I have up on the board, these numbers, represent the chances of getting a 3. Oh, it's blocked by the glare on the screen. It's the chances of getting a 3, and then the chances of not getting a 3. You have a 1 in 6 chance, that's what it says right here. You have a 1 in 6 chance of getting a 3, and then you have a 5 in 6 chance of not getting a 3 the rest of the way through. Now, just for the sake of argument, I'm going to show you something very nice in a moment. This is leading up to something. Boom. If you multiplied all of these together, you get approximately 0.096. If you multiplied all of those together, you would get approximately 0.096. Now that actually is not the answer that I'm looking for. That is actually not the answer that I'm looking for. I'm about to get the answer that I'm looking for, and then I'm going to write it on the board and then hide it from you as to which one it actually was. Yep, there it is. Nice. Hold on, because I want to see if you can figure this out. We got 0.096. The answer that we should be getting is approximately 0.386. I want to see if you can put these puzzle pieces together. Because I'm very excited for what's about to happen here. Watch this. This is the chance of getting a 3. These are the chances of not getting a 3 because we're only getting exactly 1 3. But that's not our answer, 0.096. Look at the 0.096. And now look at the actual answer, 0.386. Look what's on the board here. Look at that number, and look at this number. Say again? Multiply by 4. There are 4 distinct ways that this could happen, getting exactly 1 3. Now it's like, oh, Mr. Markey, this is just, look, what the heck is going on with all these numbers? Like, I'm about to reveal something huge to you guys. This is going to be insane. If you multiplied this thing by 4, this 0.096, you would get exactly, or approximately, I should say, 0.386, which is indeed the answer that we're looking for. Now, I don't know how this function actually works on your graphing calculator. You're going to have to show me how this works in a minute. But this complicated problem comes down to this one calculation. Look what I have up here. Look what I have up here. Binom PDF. A binom is actually short for binomial. A binomial problem is when you have a probability problem that can be broken down to a series of either successes or failures. You break it down to either a series of yeses or nos. And what a binomial distribution actually does for you is it knocks out the exact calculation that you need. Hitting enter, there it is. If you can learn how to utilize this function correctly, depending on the question that's being posed, then you don't have to do any of this legwork that I have written on the page. Instead, you can just utilize the graphing calculator. Let me see what it looks like here. Yeah, please confirm for me whether or not this is true. Hit second vars on your calculator. Hit second vars and scroll down to the function that says binom PDF. Does it show up like this on your calculator? Okay. This is important, though. This is important. Trials, P, and X value. How many times did I say we were going to roll that die? How many times? No, there were 6 sides to it, but how many times did I say we were going to roll the die to see if we can get a 3? We're going to roll it 4 times. We were going to roll the die 4 times. That's how many trials you have. What is the probability of getting a 3 on one roll? What is the probability of getting a 3 just on one roll of the die? 1 out of 6. But check this out. Look how I'm typing this in. Look how I'm typing that in. Now, when I hit enter, it's going to change it. I believe it's going to change it to a decimal. I believe it will. Oh, no, it didn't. Good for me. Did it change it to a decimal on yours? Sweet. And how many times were we looking to get a 3? How many times did we say we wanted to get exactly this many? Just 1. This is what this calculation does for you. This is what this calculation does for you. If you hit paste and enter, it does it for you. The challenge is this. If I pose to you a probability problem, I need you to be able to, number one, identify it as whether or not it is a binomial type problem. And if it is a binomial type problem, then you can utilize this function and immediately get the answer, which is nice, which is very, very nice. Now, remember you mentioned before, like I wrote out the letters Y and N, and you were like, but you can get more than 1, 3, right? Yeah, you could. You absolutely could. Watch this. Watch what I'm about to do. I'm going to mess with your heads. Check this out. Second, enter. Change that 1 to a 2. This, what I'm about to hit enter on, is the probability of getting exactly 2. of those successes. Second, enter. This is the probability of getting exactly no 3s. There's so much more to do. So, very briefly, with the time that we have, I want to write down just the definition of what it means to be a binomial. And this is what we're going to be focusing on for next week. Ah. Are you? Cool. A binomial probability, if I can spell it, has either a success or a failure. It also has a finite number of trials. The probability of success does not change from trial to trial. The beauty of a binomial probability, and this is what I was trying to exemplify. At first, it seemed like, oh my gosh, what is he even asking us? How much work are we going to have to do on this? Answer, not as much as you think. The general idea of a binomial probability is you have to recognize it as a binomial. Hey, this word problem that I just threw at you, is it a binomial problem? Well, hold on, let me check. If you read into the problem, is there only the possibility of getting a success or a failure? Yes, okay. Are there a finite number of trials? Yes, okay. Does the probability remain the same from trial to trial? Yes, then you have a binomial. And if you have a binomial, then you can utilize the function in your calculator. And it will do it for you, which is nice. Your job is to recognize it as a binomial. Let me give you an example. My parents had 4 kids. My parents had 4 kids. Oh, it's one of the... Oh, yeah, you're absolutely right. But my parents had 4 kids. I am the only boy. Feel bad for me. Feel bad for me. No? Whatever, shut up. Now, here's the question. Here's the question. If my parents were going to have 4 kids, think about this for a second. If my parents were going to have 4 kids, what is the probability that they would have exactly 1 boy? First of all, what are the chances of having a boy? 1/2. People would argue, but it's really 50%. Yeah. Does that change from pregnancy to pregnancy? No, it doesn't. It doesn't. It doesn't change from pregnancy to pregnancy. 50-50. Okay? Now, my parents just so happen to have girl, 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 boy. I have 3 older sisters. Feel bad for me. No. Now, my point being, though, what I just described. Finite number of trials? Yes, 4. Success or failure? It's success or failure, boy or girl. Yeah. Does it change from trial to trial? No, it doesn't. We get a binomial. We're going to calculate that next time. We will. We're going to talk more about my family. Anyway, that's the bell. We'll see you guys on Tuesday. She I know. Sky just said that she would have pointed and laughed at me if being the only boy. I'm sorry. Oh goodness. The funny thing is, so I'm if you're gonna leave me a little bit, like I'm the only boy, My three older sisters are much older than me, to the point where I was 9 years old. 9 years old when I became an uncle.
What, really?
Yeah,
Yo,
Oh my God.
yo.
there he is. Yeah, that's what I'm saying.
Moose was 7. Moose was 7 and he was an uncle.
Yeah, so I'm 9 years old.